when does this get interesting? Obviously the resistor had the same phase, so we don't really care that much about what the phasor says. But capacitors have a different phase, okay? So if we put a current through a capacitor, it's of course an instantaneous current, then we know that the charge on the capacitor, and what kind of charge is this? Instantaneous charge, it's lowercase q, is equal to the capacitance times the instantaneous voltage across the capacitor, okay? Well, if we want the charge, okay, then this looks something like this. So we have, this is our voltage source, that determines our frequency, okay? That puts an instantaneous current through our capacitor. The voltage across the capacitor is V sub C. So look, we know that V sub C is just VC cosine omega t, because if we're doing loop law, right, this is our voltage source, this should match the voltage source, okay? So that comes from the fact that we have a voltage source. So Q is equal to CV. Now these things are constant now. When they're capital, they're constant, okay? When they're lowercase, they're changing. So this is a capital, this is the maximum voltage across the capacitor. This is the capacitance, okay? So let's say we want to figure out the current. So we know V for our capacitor is going to be, V for our capacitor is VC cosine omega t. Okay? We know Q for our capacitor is C VC cosine omega t. How do we find instantaneous current?
Divide by R. Yeah.
Current, right, is dq dt. We take a derivative of this with respect to time. What does that give us?
Omega sine sine.
So that's going to give you negative, right, C VC omega sine omega t. Okay? Well, what do we know about negative sine? How do we write that? So let's say we have negative sine of x. How do we write that as cosine?
You start off at -1 on the y-axis.
Right. How do you write that as cosine?
You add up the phase.
You add a phase of what?
2 pi? No.
There's a pi and a 2.
Pi over 2.
Pi over 2. So that gives us cosine of x plus pi over 2. Okay, and if you don't believe me, just look up some trig identities, or you can plug this into your calculator. All right, it'll give you the same thing. So we can rewrite this as C VC omega cosine of omega t plus pi over 2. All right, and now when we look at the current across your capacitor, and we look at the voltage across your capacitor, right, these are just constants. But look at the two weights. What are they going to look like? They're going to be out of phase, okay? Now, looking at this, can you tell just visually that these are out of phase by pi over 2?
No.
I mean, kind of. I mean, this one looks like a cosine. This one looks like a negative sine. If you knew that identity, you could kind of guess that they're out of phase by pi over 2. And pi over 2 is what in degrees? 90. Okay, so they're out of phase by about 90 degrees. Okay, you can tell they're out of phase, but it's not obvious which way that phase shift is. But if you draw the phasor, okay, you first draw the current phasor, and then you draw the voltage phasor. You can draw them as 90 degrees out of phase. So this looks pretty obvious, right? V is cosine omega t. We know the angle for I is going to be omega t plus pi over 2. That means the angle between these two things is a it easy to tell what that is? Yeah, it's a 90-degree phase difference, and it looks pretty obvious when you plot it on a phasor diagram. You can see this is perpendicular to this, and these are vectors. And so we can use vector math to deal with them, okay? And so if you want to figure out what the instantaneous voltage and current is at any given time, you just plot the projection on the x-axis. You can see here we have a large positive voltage at this time. Our current is a small negative current, and that's because you have this phasor diagram that allows you to look at phase in a different way, okay? So these are your instantaneous current and voltage, and we say the current phasor, right, the current leads the voltage phasor by 90 degrees. So the current is leading the voltage, okay? And what this means is, and why does this happen? What's going on in a capacitor?
Charging and discharging.
It's charging and discharging. And as it's charging and discharging, it charges and discharges with a frequency. So it's always going to be out of phase with your voltage source, right? The voltage and current through your capacitor have this lead because as you're charging up your capacitor, right? Basically, as your voltage source goes up, it takes time for your capacitor to go up. So the current across the capacitor gets ahead of the voltage source, okay? So your voltage, your current leads your voltage by pi/2, or 90 degrees, okay? So this phase difference is introduced by the fact that there's a delay as the capacitor reacts to what's going on with your voltage source. Yes?
Would that voltage phasor determine when you're discharging or charging by crossing the x, or?
Yeah. So remember, when your voltage phasor switches sides, that determines whether you're charging in one direction or charging in the other direction. So the whole time that your input source goes up and down, your capacitor's charging and discharging. Now this gets a little bit complicated because remember, what do capacitors have when you're charging and discharging them? Think RC circuits. There's a finite amount of time it takes a capacitor to charge and discharge. So if you have a nice slow frequency, it'll have time to fully charge and fully discharge. But what if you go fast? It's going to kind of start charging, and then the polarity of the current and voltage from your source switches, and then it's going to start discharging, and then it's not going to quite have time to do that, and then it's going to start charging, right? So this is how we end up using these as filter circuits, depending on how fast the capacitor can charge or discharge, and the frequency of your input source, you get a different response from the capacitor, okay? All right, and we'll talk about that when we talk about RC circuits. But here is the question. Much better. All right, so the answer is going to be leads. And how do we know it leads? Well, they're rotating this way, so the current's always going to come just before the voltage, okay? So as these rotate around in a counterclockwise direction, you'll always see the current peak right before the voltage peaks. And you'll be like, okay, this is a circle, so like when you see the voltage peak, eventually you'll see the current peak again, but let's focus on the acute angle, okay? So the smaller angle is what we're going to determine. So quick current peak, then quick voltage peak, all right? Now this question obviously has the same answer, but is it easy to tell, looking at just the sine graphs, what you mean by lead or lag? Okay. So we're being silly, but this one still is leads, right? It's the exact same thing, just represented with a different kind of graph. And we see, look, current peaks, then voltage peaks, okay, as we go forward in time. But it's not as easy to see when you're looking at a sine graph. It's pretty straightforward that the phase is 90 degrees, and we know which thing peaks first when you look at the phasor diagram. So the whole point of the phasor diagram is to show phase in a more user-friendly way. Yes?
What would be the shift on that one?
The shift? What do you mean? Oh,
Like the phase
this is
shift.
still the same phase shift, right?
It's still a half or pi over
It's still
2.
pi over 2. So this is what the graph looks like when you look at it in terms of sinusoidal graphs, right? So this is in regular space. The phase shift is in phase space. And let me just, so at some point you guys should learn something called Fourier analysis, right? And the whole point of Fourier, I found this really cool GIF or whatever. The whole point of Fourier analysis, and for some reason it's really slow, but you'll get the idea. So look, we were talking about putting waves on other waves, okay? What this does is it breaks down all of the waves it takes to make this red wave. So these are all these little blue waves. They're just added up sine waves, right? They're all some kind of sine wave that make this red wave, okay? So this is in frequency space. Then we shift it over because all of those waves have a frequency, okay? And you see there's a big wave and a bunch of small waves. If you're talking about like radio waves, that would be your carrier wave. All the small waves, what are those? That's your information that you've encoded onto that wave. So let's say we plot this in 3 dimensions like this, so we spread out these things, okay? These peaks, these are the amplitudes, this is phase space, okay? So you can plot out what the amplitudes of each frequency are, and you can break this stuff up into smaller components that are easier to understand, okay? So what you see is that whole wave, and it carries a lot of information. The way you interpret the information, right, depends on which space you're dealing with. So frequency space, phase space, all right? So when you talk about, hopefully in linear algebra or differential equations, when you talk about Fourier analysis, that's what the purpose is, right? We're basically doing the baby version of that. Okay, we're just saying whenever you have a bunch of sinusoidal functions, you can add them up to get some bigger thing where you have signal carried onto a main carrier wave, okay? And this happens a lot. We use it for cell phones, we use it for radio, and you can break it down into phase space, which is sometimes a little bit easier to understand. And in terms of AC circuits, phase space is a lot easier to understand. What's tricky is the concept of going back and forth between them. But when you're actually just looking at the phasor diagrams, those are a lot clearer than looking at a bunch of sine waves and trying to figure out what they mean. Okay? Just a technique that we've used to figure that out. Now we're going to introduce something called capacitive reactance. Okay, and what do you think capacitive reactance is? Yes, this is how the frequency response of a capacitor. What do we mean by frequency response? Remember, capacitors have a certain amount of time they take to charge and discharge. So depending on the frequency you put in, they either have time to fully charge and discharge or they don't. Okay? So they respond to an input frequency differently depending on what that frequency is, whether they are given time to charge and discharge or whether they aren't. Okay? So look, the reactance is very large at low frequencies. Okay? And it's very small at high frequencies. Why do you think that might be? So what happens to the voltage and current across a capacitor at low frequencies? There's lots of time for it to charge and discharge. So you have big changes in voltage and current for low frequencies. If you have a low frequency, usually if you have a capacitor, even with a pretty slow time constant, you're going to have time for it to charge and to discharge, which means you have big fluctuations in voltage and current, right? So you have a big reaction from the capacitor. As you get to high frequencies, what happens? It doesn't have time to charge and discharge. So instead of these big changes in voltage and current, you get little ones, okay? So that means the voltage across the capacitor doesn't change that much because it doesn't have time to discharge and it doesn't have time to charge. It kind of just wiggles around close to the same number, okay? Because if it doesn't have time to charge and discharge, the voltage stays about the same. And that means the current stays about the same, all right? So it doesn't have time to react, and so the reactance is lower, okay? over here has lots of time to respond to changes in voltage and current. Here it doesn't, okay? So you end up with a capacitive reactance that's going to be 1 over omega, right? Omega is the frequency, times C. And this is defined as 1 over omega times C, okay? So here's the frequency, here's the capacitance. Now, we find this relationship and we can use it as in Ohm's law, okay? Something sort of similar to Ohm's law. So if the capacitive reactance is like this, what does that relate to in Ohm's law? Which variable? Reactance sounds most like which word? Resistance, okay? So if you have a voltage and a current, you can use the capacitive reactance as a resistance. So this is still V equals I times reactance, okay? So in AC circuits, reactance is a lot like resistance, and we can use it to figure out the voltage-current relationship, okay? Now what else do we know about voltage? Now, these are the maximum current and maximum voltage. What do we know about the instantaneous current and voltage? Can you use V equals IR for that? No, why? They're out of phase, right? So do this and this happen at the same time? No, okay? These things peak at different times. So this only works when you use the maximum values. This is the maximum voltage across the capacitor. This is the maximum current across the capacitor. But they don't work, they don't happen at the same time. So it's very important to remember when we use the uppercase stuff, right? This is not for the instantaneous value. At any particular time, your voltage and current are not related like this. Okay, this is just telling you how your peaks are related to plot the graph. Yes?
So why are you using it as a resistor and not caring about the discharge portion of it?
So this includes discharge, right? This is just how, so we're looking at the big picture. We're not looking at how the capacitor's charging and discharging. We're looking at when it's charging and discharging related to its time constant, right, which is included in C a little bit. Depending on what frequency we put in, how much time does it have to respond? Okay. So you can see if you have a bigger capacitor, right, that's going to give you a smaller reactance. Okay, because what do we know about a bigger capacitor?
It needs more time.
It needs more time, right? So it's going to be more responsive to the frequency. So if you have a faster frequency, that's going to mean that it's gonna have less time to respond, and it's not going to work as well. So it includes both the frequency and the capacitance for a reason, right? Bigger capacitor means lower reactance. Bigger frequency means less reactance. Okay. Now this is plotted in terms of frequencies. You can see as the frequency gets bigger, no matter how big the capacitor is, it has less time to respond, and it's going to have less resistance. Okay, because you're not going to change your current and voltage very much. Yeah. Okay. Here's a question.
That's so funny.
Yes, so it's half. Okay, please discuss. We'll vote again.
Because it's 1 over C still. Right now. Okay, you double the capacitance again, which gives you a half, and you multiply it by I, so your I is half. Let's see.
It's 1 over 1 half X. Plus this.
Yeah, just split.
But you have 2. So it's 1 half X.
I don't think that's effective at chalking your hands.
No.
Yeah, I see what you're saying. Oh, you're right.
So take it back. V over 1 half X.
Should have used torque.
This is a half.
Yeah, okay.
All right.
Yeah.
Another couple seconds.
Vote again.
Make sure you voted again. lost somebody. Yes. So, if you have the reactance, what happens to the current?
Double.
It's doubled. Okay. So if you have your reactance, you double your current. Okay. In order for the voltage to stay the same, if this goes down by half, this has to go up by 2. All right. So yeah, that's what that looks like. So we're gonna try just a quick. Actually, I think we're kind of out of time. Yeah, we have 6 minutes. All right, we can do this in 6 minutes. So let's talk about capacitive reactance with some actual numbers. So let's say we want to know the capacitive reactance of a 0.1 microfarad capacitor for 100 hertz audio frequency and also at a 100 megahertz FM radio frequency. Okay, and this is just plugging in numbers, so we're going to do this together. I need an eraser. All the erasers are gone.
It's not in the budget.
It's fun. All right. There's an old, really old, terrible eraser in here. So we'll try that out. Yeah, that's going well. I think we didn't have very many problems today. Somebody stole all the erasers.
Wow.
And the chalk. All the chalk's gone. Anyway, oh, that thing is gross. All right. So we want to know the capacitive reactance. That's 1 over omega C of a 0.1 microfarad capacitor at 100 hertz audio. So this becomes 1 over, what do we know about omega? 2 pi times, is that omega or F? F. So 2 pi times 100 hertz times the capacitance, which is 0.1 times 10 to the negative 6 farads. Okay, so that's going to give us a value of 16,000. And what units is this in? Ohms. Okay, remember we can plug it into Ohm's law. So, ohms. Alright, so it acts as a resistance. Okay, for the other value, that's going to be 1 over 2 pi times 100 megahertz. So 100 times 10 to the 6th hertz. This is 0.1 times 10 to the negative 6 farads. So you can see 10 to the 6, 10 to the negative 6, those go away. So you end up with 100 times 0.1 times 2 pi. And this should give you, I think, 0.016. So you can see the same capacitor is very frequency dependent. If we have a large frequency, you get a very low resistance. If you have a small frequency, you get a really high resistance. We go from 16 kiloohms to 16 milliohms. Right? Very different. Let's try a problem. We have a 10 microfarad capacitor. 100 hertz oscillator with a peak of 5 volts, and we want to know the peak current of the capacitor. So the first thing we want to do is figure out the capacitive reactance, okay? So the capacitive reactance is going to be 1 over 2 pi times frequency C, because it's asking for omega, but what are we given?
Wow.
1,000
1,000 hertz.
hertz is frequency, right? Frequency F, not angular frequency omega. So you have to make sure you don't forget the 2 pi. Okay? So this becomes 1 over 2 pi times 1,000 hertz times the capacitance, which is 10 microfarads. So 10 times 10 to the negative 6 farads. Okay? And this gives you 16. 16 what? What unit?
Radian.
Oh,
Oh.
okay. Which, I mean, well, it's not like super obvious, but radians per second times farads apparently is inverse ohms. So good look at that one. But the main thing to remember here is, what is this? The reactance is a kind of resistance. Okay, anytime you have a resistance, it gives you ohms. Alright? So now we have our resistance, and if we want to figure out our peak current, right, we say IC is equal to VC over X sub C. Now what determines what the voltage will be across the capacitor?
The instantaneous.
The voltage source, right? Usually, it used to be the battery, now it's this squiggly source. Alright? So we have 5 volts divided by 16 ohms, and this should give you 0.314 amps. Okay? So that's 314 milliamps. Alright? Any questions about that? Cool. So we're still using Ohm's law. We're just trying to figure out how to deal with resistance in this new world of AC circuits. And remember, Ohm's law now only applies to peak current and peak voltage, which when you're looking at your sinusoidal graphs, right, those are these values. Okay, just the maximums, just the peaks of